Today we're going to talk about LeetCode question number 543, diameter of a binary tree. So given the root of a binary tree, return the length of the diameter of the tree. Diameter of a binary tree is the length of the longest path between any two nodes in a tree. The paths may or may not pass to the root. The length of the path between two nodes is represented by the number of edges between them. Okay, not number of nodes, number of edges. So for example here, the longest path would be this guy of 1, 2, 3 edges. Okay. Oops. Yeah, this could also be a path, but same number, 3 edges. Okay. Let's look at another example where the longest path doesn't cross the root. So if we have like here, this, and these have children, and this. Okay, so in this case, the longest path would be between this node and this node. Okay, so it'd be 1, 2, 3, 4, 5, 6 edges. Okay, and if we decide to pass to the root, it'd be 1, 2, 3, 4, 5 edges. Okay, and 6 is obviously greater than 5. So our longest path between any two nodes would be this guy here. Okay, so how do we determine the longest path here? Okay, what we could do is go node by node, like, start at this node here and count its longest path between two edges. So this has no children, so the edge count here would be 0, and here the edge count, the maximum edge count I should say, would be 1, 2, 3, 4, 5. 5 plus 0 is 5. Okay, so the edge count for this node would be 5, and then we go through each node below it and do the same thing. So if we look at this node here, count the maximum number of edges on its right side, 2, and on its left side, 1, 2, 3, 4. Okay, and then we get 6. And that's a possibility, but it's not very efficient as we kind of redo work here. So for example, if we were looking at this node, we counted all the number of edges for this guy already. Okay, and here. But if we were looking at this node now, we count the number of edges here and here. So we're kind of duplicating work here. So in this case, what do we do to make it efficient? How do we visit each node at most once? So what we could do instead is traverse all the way down to its children. Traverse all the way down first until we hit our base case in our depth first search. Okay, so in this case, this guy's children would be none. Okay, traverse all the way down first. Okay, and then for this guy, for this node, calculate the diameter. Okay, so in this case the diameter would be 0. Let me write that better. Diameter would be 0. Okay, and then we bubble up. Okay, we're recurse up, and using the results we found here, we can determine this guy's maximum diameter. Okay, so and we would keep track of these diameters in like a global variable or something. Okay, to determine the max diameter. But what exactly do we return to this node? We can't return the diameter result for this node. Okay, this child is not this node's child. What exactly do we bubble up? So what we bubble up exactly is the longest length we see so far, the maximum depth we see so far for this node. Okay, So if this node has like all these children here and it has like no children here, then what we want to do is for this guy return the depth length of 3. Okay, and it makes sense because we want the maximum depth to be the longest depth to be part of this guy's diameter calculation. Okay, while we want the smaller depth. Okay, so that's how we're basically going to go about it. And in terms of counting number of edges, so our base case will be, we're going to use D at depth first search, and what the base case will be would be if the node is none, then return -1. Why -1? Why not 0? Well, it's kind of convention, especially when you count in number of edges instead of number of nodes, we return -1, and it makes sense, right? Because this has none, this has none, we return -1, we return -1. Okay, and to get the diameter, okay, we would do, this node left plus right plus 2. Okay, why 2? Because we're counting these edges here. Okay, so we have to add by 2, this left edge and the right edge. So it's 1 plus 1, left edge and the right edge. Okay, and that's how we're going to calculate the diameter. And what about when we bubble up here? So what exactly do we bubble up? So what we bubble up is, so this node's edge or number of edges is -1. This node's number of edges is -1 because there are none. Okay, and this node's number of edges is 0. So what do we bubble up here? 0 plus 1. Okay, because we want to count this edge. Okay, so that's what we bubble up to this node. Okay, and that's basically how we're going to go about it. Now to code it up, so what we're going to do now is have our result variable, our global result variable here, and then define our recursive helper function. Instead of having a global result variable, we could have, just returned maximum, somehow return maximum depth, but I find this easier. So what we're going to do is define our base case. So if root equals none, return -1, because nodes that are of none value, okay, none nodes they don't have a number of edges 0, okay, so this node would have 0 edges, basically, like branching out of it. The nodes of none, they have -1, okay, not 0. Else what we're going to do is left is equal to helper left, right is equal to helper root dot right. Okay, so this is basically pre-order traversal, okay, where we, post-order traversal, where we visit the children first and this guy and the parent last. And remember, we're doing this because we don't want to do any duplicate calculations, okay? So we're calculating the children first, very last leaf nodes first, and then bubbling up the results. So you visit each node at most once, okay? And then calculate diameter. So now that we have the number of edges between the left and in the node's left pointer and in a right pointer here. We're going to calculate the number and put in our result variable. So result 0 is going to be equal to max result 0 and left plus right plus 2. Okay. Remember, why is it 2? Because if we were at this node here, this guy's number of edges would be 0, this guy's number of edges would be 0, this guy's number of edges would be 2, 1, 2. So we do 0 plus left edge plus right edge. Okay, 0 plus 0 plus 1, which is plus 2. Okay. Okay, and then once we update our result variable, if you needed updating, well, we're going to return longest edge. So we're going to return is the max left plus 1 and right plus 1. Okay, left plus 1 and right plus 1. Okay, and if we were at 4 and we want to bubble, we will curse up back to 2. So it'd be this guy's number of edges would be 0, so we want to bubble about number of edges 1 because we want to include this edge here. Okay, and that's pretty much it. And then I'm going to call the helper function and turn result. Okay. And yeah, looks good. I'll try submitting it. Okay, and this is O of N runtime with O of H space complexity because of the recursion stack here. Thanks for watching.